All right, so we are now on to the last section of this probability and statistics, and that is hypothesis testing. So we can use probability to test our hypothesis. So a hypothesis is a proposed explanation for a phenomenon or a question, and then we use probability to decide whether or not the hypothesis is valid or not. So we might say, for example, look at IQs of a certain group of people, and we might say, well, there's a number of different hypotheses that we could say. They could be the same as the IQ of the population, they could be less or they could be more. And so what we then do is use that hypothesis, and then we use some statistics to see whether our hypothesis is any good or not. All right, so there's a thing called the null hypothesis. So the null hypothesis is basically what it says is that the group we're looking at is the same as the whole population. All right, so that I guess that's then our starting point, and it's called the null hypothesis. And we always work, when we're doing a hypothesis, we always work with this null hypothesis as being that this group is exactly the same as the population. And so here's an example. So the population IQ, that's the way IQ is worked out on, is that it's 100 is the mean score, and standard deviation is 15. And so the null hypothesis says that any group from that population will have the same mean. So for example, our special maths class, the null hypothesis says the IQ of the people in our, or the mean IQ of the people in our special class is exactly the same as what the population is. So that would be the null hypothesis. Then you come up with an alternative to the null. So an alternative hypothesis, H1, it says there's a variation, and that variation is significant. All right, so in other words, that the sample group is different to the population. So we have to have, when we do the statistics, we have to have a statistical difference that's significant. Not like we've looked at those margins of error and confidence and fitting in that. Well, for our alternative hypothesis, it's got to be outside of that to be true. It's got to be outside of that. So an alternative hypothesis might be that our special class, the mean IQ of the people in our special class is greater than 100. All right, so, and here's another. So a group of university lecturers has their IQs tested and the mean is 109.6. And the hypothesis is that the mean of this group is different to the population for some particular reasons. All right, so the group of university lecturers, if you like, is a sample of the whole population, and their IQ, it comes out to 109, which obviously is greater than 100. But you could still say, oh, well, that just happens to be that particular group at that time. So you might test it another time, and so it's not significantly different. That would be the null. But then the alternate hypothesis, H1, is that no, that this group of people, their mean is statistically different from the whole population. All right, and so we use statistical measures are used to test our hypothesis. And one of them is called, this thing here is called the p-value. And the p-value, we work on the assumption that the null hypothesis is correct. And then we have a look at this p-value, and this value that we come up tells us, based on assuming that the null hypothesis is correct, that whether that is the case or whether it's not statistically. So for example, so H0, it says that the mean of this particular group is the same as the mean of the population. And so the alternative hypothesis would say that the mean of this group is greater than that of the population, whereas the mean of this group is the expectation value of the sample. All right. And so the expectation value of the sample, this is using the null hypothesis, of course. So that's this one here. That the expectation value of the sample is the same as the population, and standard deviation of the sample is this based on the population. And so the p-value is a probability. So it says here the probability that the sample is greater than or equal to x, given that the mean is 100. So the probability that the mean of our sample is bigger than, given that the mean is 100. And this is how you work it out. It's a probability thing, z greater than or equal to x bar minus the mean over the standard deviation of the sample. See here, x bar. So it's standard deviation of the sample. All right, so here is a couple of examples that kind of illustrate that stuff. So here we go. The average fuel consumption of a particular model of car is 13.7 litres per kilometre. The manufacturer is claiming that the new model will use less petrol. All right, so the old model, the fuel consumption, the old model, which is the population. All right, so the old model, we'll just call it model, and that's the population. All right, the mean there is 13.7 litres per 100 kilometres. Now the new model, new model, where they even use the word sample of 25 of new model cars. So that's our sample. Its mean is 12.5. All right, so write down the null and the alternative. All right, so the null hypothesis So the null one, H0, what that says is that our mean is equal to 13.7. So the mean of our population is exactly the same as, the mean of our sample and the mean of our population are exactly the same. That's of this. And so we're saying that even though we've got a sample and our sample says 12.5, if this new model, we were to produce thousands of them and test them all, what we would end up with is a mean fuel consumption the same as this one, as this population. The alternative hypothesis, though, says that the mean of these new ones, this number here, is 12.5, and so we're saying actually this new model, the sample, is representative of a population of the new model, and it's going to be less than that one. So in this case, we're going to compare our new model with our old model, so we can say, the manufacturer's going to say, oh well, our new model is more fuel efficient than the old one. So we want our new one, we want that to be less than 13.7 as our alternative hypothesis. And then we need to test those. All right. So when we test those, this is example 2, which is what we've just talked about up there. All right, so what have we got? We've got some stuff here. Assume that the fuel consumption is normally distributed with a standard deviation of 2.8. The average fuel consumption of the cars is 12.5, and we want to determine the p-value for this test. All right, so p-value. Remember what the p-value is. The p-value is, whoops, here we are. Let me write just looking on this sheet for the p-value, is the probability that Z is less than or equal to, no, greater than or equal to, not less than, Z is greater than or equal to our sample mean minus our other mean over the standard deviation of our sample. So let's have a look at our population. All right, so our mean of our population, we know that's 13.7. All right, because that's what our null hypothesis says. It's exactly the same. Excuse me, our standard deviation of our population is 2.8. And now we've got to work with that. All right, what do we need here? We need our sample mean. And here's our sample mean. We've got that there. All right, so our sample mean, X bar, we know that's 12.5. And what we need is our standard deviation of our sample. Now, standard deviation of our sample is our population mean over the square root of our sample size. And of course, our sample size was 25, wasn't it? 25 cars, there it is. N. So standard deviation of our sample then is 2.8 over the square root of 25, which is 2.8 divided by 5, which is 0.56. All right, so now we're looking for our, excuse me, our p-value. And so our p-value is the probability that Z is greater than or equal to, less than or equal to, not greater than or equal to. In this case, is that because we are, so I've copied it down from a previous example where we were looking at something being bigger than, but here this 12.5 is less than, isn't it? So in this particular case, that's what we want to know. We want to know what is the probability, effectively, what is the probability that this value that we've got here is in fact going to be the case. All right, so we want it, and because we're trying to promote this car as being more fuel efficient, all right, there we go, less than, more fuel efficient, we want less than. All right, I've just covered that up. All right, so less than or equal to X bar, which is 12.5, minus the mean, which is 13.7, over 0.56. And so we're looking at then that the p-value, the probability that Z is less than or equal to negative 2.143. All right, so then we get our calculator out. And so let's get our calculator. Here it is. I don't want that. I want statistics. I want to calculate something. I want to calculate, I'm doing a test. I'm testing. What am I testing? I'm testing, this stuff that I've just looked at. One sample Z test, that's what we want, Z test. So P-value, Z test. You notice there's a Z in the formula. Variable, I want to go variable. Then we go next. All right, condition. So in here, we're saying that our new mean is less than. So we want less than. All right, so here, this is what we're testing. We're testing that it's less than. All right, so we put the less than there. New 0. So that's our null hypothesis mean. So that's, what was that, 13.7. You can go help if you want. Null hypothesis. So population mean. Standard deviation. Population standard deviation was 2.8, wasn't it? 2.8. There it is, poking out there. Our mean of our sample, there it is here, X bar, and that's 12.5. All right, so we don't actually even need the Z value here on this one, all right? And then our sample size, that was 25 cars, wasn't it? All right, so then we go, all right, next, and here we come. So there's our Z value, negative 2.14, so that's what we did before. And here it says the probability is 0.0161 to 4 decimal places. So that probability, the probability that oops, that's not what I want. The probability, the p-value is 0.0161. Now that's a very low probability, so in terms of percentage, that's about 1%. So when we're saying that our new car is going to be more fuel efficient than the old one, well, based on this p-value here, it says there's only 1%, which is not a very significant difference at all. All right. All right, so what does it mean? How do we interpret? All right, so there's the calculator stuff there. I did put that in. So what does it mean? So in terms of, so this table here really handy, and this is what you need in your bound reference. So what does it mean? In general, the smaller the p-value, the greater evidence against the H naught. All right, so we had, what did we have? We had 0.01. So 0.01, so I'm saying strong evidence against. Well, actually, it's between those, isn't it? So good evidence against. So in that, from based on these value that we've got here, based on these figures and our sample of 25, it's actually what it's saying is, yeah, there's pretty good evidence that the new model is actually going to be more fuel efficient based on this. So this p-value in conclusion, I think I was a bit vaguer up there when I was talking about that. When I said 1% is not a significant difference, but in fact it is significant in that we're looking at the the bell curve, this 1% here is down here in this bottom 1%. So if that's all our population and our new model, well, our sample is our old model, our sample's actually putting our new model way down here, right, way down the bottom. So if this is our H0 line here, and we've got something way down the bottom from our sample, then that's why it's saying here, well, that's good evidence, strong evidence against H0. So what was H0? H0 was that the new model's fuel consumption is exactly the same as the old model's fuel consumption. But because we've got that p-value probability value way down that bottom end, it's actually some pretty good evidence that it might be more fuel efficient. All right, so sometimes they're referred to as statistical significance. So statistically it's a significant value. Sometimes you hear that in news reports and things. And say, for example, we're looking for a 5% significance. It means you're looking for a p-value less than 0.05. All right, and so sometimes we say the significance level of a test is often written as alpha, and alpha is 5%, means a p-value of less than 0.05. That's just an interpretation of what those wordings mean. All right, so yeah, hypothesis testing. It's kind of a bit of a strange thing, but in a way, but basically, because we're taking samples and we want to try and then use that sample to make predictions on things, we use this p-value to see whether our sample is significantly different to what the population is. All right, and so in the example of the car, for example, you got your old model and you got your new model. What is it that we think? We think our new model's more fuel efficient than the old one. So we do come up with this p-value, and because we found it's down 1% significance, then that then supports the idea that, well, yes, it is more fuel efficient than the old model. All right, so that's it for that section, the first part of the hypothesis testing. So if you've got questions about that, get back to me and have fun with all the hypothesis stuff.